last time we already started to discuss optimization problems. So we will see today a few more examples. Okay, so this is essentially one reason why we have developed the results for differentiation we have developed so far. Namely, what we want to do is we have a given quantity and we want to optimize it. This is obviously something which is important in applications. Like if you work in a company, you might be interested in optimizing the profit of the company and so on and so forth. So there are many obvious examples where optimization problems occur in applications. And we saw already last time a general strategy how to solve them. So as I have explained last time, normally the first thing if you encounter such a problem is to plot the diagram or to plot the situation, to make a picture. Then the second step is to introduce notation. Then normally, you have one quantity which you want to optimize. Normally, you can express this quantity in terms of all the other quantities. And since we can only handle functions of one variable, we have to try to eliminate all the additional variables so that our quantity which we want to optimize just depends on one variable. And then the rest is more or less the tools we have developed. So we know that the rest is just finding, in terms of optimization problems, very often absolute extrema, so absolute maximum value and absolute minimum value. So normally, we know, for instance, the situation is most easiest if the function is given on a closed interval, because then we have the so-called closed interval method. So in this case, we just look at the critical points. So we take the derivative, compute the zeros, and include all points where the derivative does not exist, so-called critical points, and evaluate the function there, and evaluate the function at the two boundary points, and just pick the largest or the smallest, depending on the problem setting. If the function is not given on a closed interval, we need other methods, because we are here interested not in local extrema, because previously most of the time we have discussed local extremas. Here we are interested in global extremas, but we saw that, for instance, last time we saw an example of a function which is not defined on a closed interval, but we have observed that at some point, for some points to the left of this point, the function is always decreasing, to the right always increasing. Then, of course, we do not even have. It's not only that at the point we have a local extrema, but also a global extrema or absolute extrema. And you can find this in our textbook. There is a result which is called the first derivative test for absolute extreme values. This is just what I said. But as I have emphasized also last time, it's quite often clear from the problem setting that either a local extrema or a local maxima exist. And so the normal way to do it, if it is clear from the problem setting, we just compute the derivative of the function to optimize equated to 0, and if there is only one root, and we know there must be a solution to our problem, then we do not have to discuss whether at this point the function really takes on absolute extrema, because we know already from the problem setting that this must be the absolute extrema. Now, last time I showed you some simple examples, so maybe let's discuss not very complicated ones, but maybe examples where you have to think a little bit more. So, for instance, let's assume that we have two poles. Let's say one is 5 meters high and the other one is 2 meters high. And those two poles stand in a distance, within a distance of 3 meters. Okay, now you have a rope which is fixed to the ground, and the rope is going up to both poles. So let's say this one and this one. Okay, and what we are interested in is finding the point P such that this angle here is getting maximal. Okay, so find P such that theta is maximal. Okay, so as I have said, the first step is to introduce notation. Here it's pretty clear that, okay, so we will call this here x, and then this length is 3 minus x. Now, it seems to be slightly more easy here to look at alpha and beta. And instead of maximizing theta, what we're going to do is we minimize alpha plus beta. So that's the same problem. So we minimize. We try to minimize alpha plus beta. So this is a very easy example, but this approach is pretty general. So sometimes it's not the most intelligent thing to do to maximize, for instance, here the quantity you have to maximize, but instead define another quantity which you either maximize or minimize. Here, minimize. Now, you see that alpha plus beta is easily expressed in terms of x, because you see that alpha is equal to the arctangent of 5 over x, and the beta is equal to the arctangent of 2 to the 2 over 3 minus x. Okay, so this is now already our function which we have to minimize, and you see this function just depends on one variable. Moreover, you see that this function, so our problem is the problem of minimizing this function on a closed interval, namely x can be between 0 and 3. Okay, so observe that it looks like this function is, the function f of x is not continuous on the whole interval. For instance, if x is equal to 0, the function is not defined there. But if we define the function f of x suitable for f of x, for x is equal to 0, namely just by choosing the limit as x tends to 0, so we have here pi half plus the arctangent of 2 over 3, okay, then with this definition, the function is getting continuous on the whole interval. So actually, we can say the function is continuous on the whole interval. And in order to find the smallest value, we can use now the closed interval method. Okay, so we just, in order, because we want to know we want to use the closed interval method, so we have to check the function value of f at the two boundary points, 0 and 3, okay, which are defined as the limit, and at the critical points. So for the critical points, we have to take the derivative. So the derivative here of the arctangent, as we know, is 1 over 1 plus 25 over x squared times, so this is the derivative of the outer function times the derivative of the inner function, plus the same here. So here you have 1 over 1 plus 2 over 3 minus x squared times the derivative of the inner function, which is okay, so actually we have a minus, but because of this minus, it will be plus. So we have 2 over 3 minus x squared. Okay, so this is the function we have to, or this is the expression we have to equate to 0. In particular, you see already from this expression that that the derivative, because we are searching for the critical points, the derivative exists everywhere. Also for the two boundary points, we do not have to consider. So the only critical points are the points where the derivative is equal to 0. Okay, so x is in 0, 3. Now we have to do some computation. Okay, so minus 5 over x squared plus 25 plus, and here we have 2 over 3 minus x squared plus 4. Now this is equal to, so common denominator, x squared plus 25 times 3 minus x squared, 3 minus x squared plus 4. Okay, so we have here a minus. Now, so we have x squared, so we have minus 5x squared. Then we have minus 6x. With this minus 5 here, we have plus 30x. Then we have here 9 plus 30, so times 5, so minus 65, plus 2x squared plus 50. Okay, so you see that because we have to equate this to 0, so you see that because this is here the minus 15, 30x, and minus 3, so we can take out minus 3. And the rest is x squared minus 10x plus 5 over x squared plus 25. And here we have, okay, this is not important, so 3x squared plus 4. So we have to equate it to 0. So from here we see now that we get two solutions. It's 10 plus minus the square root of 100 minus 20 over 2. Okay, so you have these two solutions here. You will observe that one of them is negative, so one doesn't make sense. So you can forget this solution here. None of them is negative, but one is too large, because 1 is obviously larger than 5. The plus solution is larger than 5, so we can forget about this. The plus solution. Okay, so because you see that the x must be between 0 and 3, only the other one satisfies that the x is really between 0 and 3. And now you check those two, so that you have one critical point here, and you have the two boundary points, and you plug the 3 points into the function f, and you will observe that this, the second solution here, so this is 5 plus minus. You will observe that this solution here is the minimum value of the function f. Okay, so here you still have to compute so this is the value we keep. Okay, so now compute f of 0, compute f of 3. These are the two boundary values, and compute f of 5 minus 2 times the square root of 5. Okay, and you will observe that this here gives the smallest value. So by the closed interval method, x is equal to 5 minus 2 times the square root of 5. The minimum, the absolute minimum is achieved. Okay, so you see here, this is another example for an optimization problem. This example should show you that sometimes it's easier to minimize or maximize a related quantity. So this is a basic idea which quite often can help in solving more complicated optimization problems. Also here you see that once more, for optimization problems, we are always interested in finding absolute extrema. Now, if the function is continuous, if you have a continuous function on a given interval, then a closed interval, then essentially what you use, unless it is clear already from the from the geometric setting that there must be absolute maximum, absolute minimum of the involved quantity. So you can also argue here by geometry, so it should be clear from the geometric setting, but maybe this is more complicated. Normally you have also to check whether the zeros of the derivative are really absolute extrema, because we know in some cases maybe the absolute extrema are taken on the boundary. Okay, because I know from experience, students, if they encounter such a problem, very often they just compute the derivative of the quantity equated to 0, and if there is only one solution, they say, okay, this is the solution. Okay, but you have to be careful, because sometimes the absolute maximum and absolute minimum, depending on the question, is not taken on at the 0 of a derivative, but maybe at the boundary. So you really have to discuss, okay, whether all your critical points, at which of your critical points you have your absolute maximum or absolute minimum. Okay, so this is another example. Now, maybe a few more examples. Maybe a slightly more interesting example, also from the point of view of applications, is Snell's law of reflection. Now, it's something which you have learned in physics. So if light is traveling from this point here, A, to some other point, B, and gets reflected at some media, for instance, light is traveling like this here, then gets reflected at this media here, then you know that, okay, if you look at those angles, okay, so this is alpha and this is beta, then you know that alpha must be equal to beta. Okay, this is the so-called Snell's law of reflection. Now, wait, let's just use this notation. Okay, so maybe let's just introduce some notation. So this I call H1. This I call H2. Then let's say this is X here, and the whole length is L. Okay, now the first question here is, okay, so what I want to do is I want to prove Snell's law of reflection. Okay, so I want to prove that if light is traveling from point A to point B and gets reflected at some media, okay, then I want to prove that for those two angles I must have that alpha is equal to beta. Now, here it's not so obvious why this is related to an optimization problem. Okay, but maybe in physics you certainly have learned that there is a basic principle called Fermat's principle. Now, what does Fermat's principle tells us? The path which light chooses, okay, minimizes time. Okay, so the path which light chooses minimizes time. Okay, so the way light is traveling from A to B is in such a way that the time it takes to go from A to B will be as small as possible. So because of this principle, it's the problem of proving Snell's law of reflection essentially is the optimization problem. Okay, since you know that the speed of light, okay, is like you can consider it as a constant. Okay, so it's to minimize the travel time or to minimize the distance traveled is just the same. Okay, so what we have to do is we have to minimize d. Okay, so we have to find x such that d is getting as small as possible. Now d is the length here from here to here, which is easily computed by Pythagoras theorem. So you see that you have the square root of h1 square plus x square for this part here, and for this part you have the square root of h2 square plus L minus x square. Okay, so instead of minimizing the time which light needs to travel from A to B, okay, we minimize the distance. Okay, it's the same because the distance and the time are related by the speed of light, which is about a constant. Now you see, okay, so we have to find the x essentially. So now we are really in the domain of calculus, and the rest is just calculus. So the question just becomes, okay, for which x is the distance getting minimal? And for the x which solves this, okay, we will have that the alpha is equal to beta. This is the only thing we have to prove. Okay. Now, okay, so we take the derivative here. So you see you have here x over the square root of h1 square plus x square plus, and the derivative of this one, so this is 1 over, you have 2, so minus L minus x over the square root of h2 square plus L minus x square. And you have to equate it to this to 0. Okay, so this gives x over the square root of h square plus x square is equal to L minus x over the square root of h2 square plus L minus x square. Okay, so actually we have to solve this for x. We do not really have to do it because we do not want to find this x. We just merely want to prove that for the x, minimizing the travel at the distance, okay, alpha must be equal to beta. Now you see that in terms of alpha and beta, for instance, if you look at this one, okay, you see this is x over this length here, but here you see alpha as well, and here you have beta as well. So actually, this just tells you that the sine of alpha, if you rewrite this, then you see the sine of alpha must be equal to the sine of beta. Okay, so this just means that the sine of alpha must be equal to the sine of beta. Now you see that both angles, alpha and beta, are between 0 and pi. So you also know that alpha and beta are both between 0 and pi half, actually. And for this range, okay, this equation just has one solution, namely alpha is equal to beta. Okay, so from here you see now that alpha must be equal to beta. And this already proves our result. Okay, so you see that proving such laws, there are more laws of reflection and so on. In our textbook, you see more examples. This is essentially one of the examples in our textbook. Here, in order to prove something like this, it's maybe unless you know this, it's not so clear that this is really an optimization problem. But once you know this basic principle, then actually proving Snell's law of reflection just becomes an optimization problem, and that's the only thing we have. And for optimization problems, we can use our approach. If you set up the problem in an intelligent way, you can sometimes avoid using the theory of integration. You can immediately figure out how to optimize some given quantity. Now, in our textbook, you find an example where you have you are asked to inscribe a rectangle into a semicircle of radius r, such that the maximum is getting the area is getting maximal. Okay, so you have a semicircle. You have to inscribe the rectangle into the semicircle such that the area of the rectangle is achieving a maximum. Now, the first thing you do for such an example, you choose a coordinate system. Okay, normally you will choose the coordinate system as easy as possible. So you will put the center of the semicircle into the origin of the coordinate system. Everything else would be too complicated. Okay, this is pretty clear. So you have your we have our semicircle, and we place the semicircle such that the origin is in the origin of the coordinate system. And then our question becomes, okay, so find the rectangle like this. Find the dimensions of the rectangle such that the area is getting maximal. Now, actually, something which doesn't make a big difference here, but which is maybe sometimes helpful in such geometric problems is if you have given that the radius is equal to r, okay, of course you can assume without loss of generality that the radius is equal to 1, which sometimes makes the computation more easier. Okay, you just shrink the whole thing, okay, by a factor 1 over r. So actually we can assume that the radius is 1. Okay, so we do not have to work with it. If you have such an exercise, okay, it's geometric, it's such a geometric example, and you have to prove either to prove something or to get the maximum, okay, normally you can shrink it, okay, and this will not, of course, this will shrink the maximum by a factor of, so you have by a factor of 1 over r squared, okay, so the maximal area you get by shrinking it, okay, you have to multiply it then with r squared, and you will find the original area, okay, so since we have placed the coordinate system like this here, we assume that this point here is equal to xy. And now, of course, you can set up the problem. So you can you have that the area is equal to 2x times y, and you have for x and y that x squared plus y squared is equal to 1. You remove one variable. You plug it in, you take differentiation and so on. So this is just the standard approach which we just have used before. So you use the method of differentiation in order to do this. But maybe so for this example, I'm not going to do this. You find this in our textbook. So the standard approach would be if you introduce the notation like this here, then the area is equal to 2xy. Okay, so the area depends on two variables. But you have, since this point is on the circle, so you have another condition. Okay, so you see from this condition that y must be equal to the square root of 1 minus x squared. You plug this in here, and you take the derivative. Okay, the x is on the function. So you have 2 times x times the square root of 1 minus x squared. Okay, you discuss the function on this interval here, so you have a closed interval, and you can use the closed interval method. Now, this is not the best way, okay, to do this example. For this example, you can completely avoid going into the theory of differentiation just by setting up the problem differently. Okay, and setting up the problem differently, for instance, one other possibility is to choose this angle here as your main parameter. Okay, so you do not look at this point here. Okay, so if you do this, you see that this length here is the sine of theta. This length here is the cosine of theta. Okay, and you see that the area now becomes 2 times the cosine of theta times the sine of theta. Okay, but this is the sine of 2 theta. Okay, and this here, to maximize this is very easy because we know that the sine is getting maximal if theta is equal to, if 2 theta is equal to pi half. So you get immediately theta must be equal to pi over 4. Okay, so here you do not have to use differentiation, and now you easily get here for this dimension. So you have here, so the sine of theta. So the maximal area must be equal to 1. Okay, or for the general example where you have a general radius r, the maximal area is equal to r squared. So you see sometimes, this is just an easy example, okay, but sometimes because you have different choices for your notation, okay, you can differently look at the problems, and for some geometrical problems, by intelligently choosing the parameters, okay, sometimes it's possible to completely avoid the theory of differentiation and still being able to solve the problem. But of course, this is more tricky, okay, not for this example. For some examples, it's not so easy to think about something like this here. You can always do it like this, and this is the standard. You just use the standard tool. So it's of course not much more complicated. But on the theoretical, from the theory, okay, you have to use differentiation, whereas here you can completely avoid it. So this is something you can do already, even if you haven't learned the theory of differentiation. Now, 4.10 is essentially just introduces a notation, which are the so-called antiderivatives. This is a very easy and very natural concept. Until now, we always talked about we always had a function, and we were interested in the derivative. Now we are kind of interested in the inverse problem. Something which is obviously important also from applications. For instance, it might happen that you know the velocity of some particle and you want to know the position. If the velocity is constant, okay, it's very easy. You just multiply it with the time traveled. But if the velocity is not constant, okay, it's a more complicated, can be a more complicated problem. But you know that since the velocity is the derivative of the position function, what you have to find is actually just a function whose derivative is the given velocity. So it's the inverse question. Now, for a given function, if you can find another function whose derivative is the given function, this other function is called antiderivative. So that's the definition. Okay, so f of x is called antiderivative of f of x if the derivative of this function is equal to our f of x. Okay, so this is antiderivative. Now, from this definition, okay, we have already several good questions. What is a good question here? If you see something, a definition like this, which question pops up in your heads first? There are several. You can ask several questions. You do not have any questions. Several questions. The first question, for which function? How can I, if I have a function, how can I see that such a function has an antiderivative existence? So for which function do I have an antiderivative? Okay. If I solve this problem, existence, how to find the antiderivative? Is there a good way for a function? Okay, I know, for instance, all continuous functions have antiderivatives. Okay, how do I find the antiderivative? Second question. The third question is how to find all. Okay, so already from here you have several good questions to ask. Okay, the first is for a given function. How can I, just by looking at the function, how can I decide whether this function has an antiderivative or not? The second is okay, if I have some easy criteria, like if I know for all continuous functions there exists the antiderivative, and we will prove this later is indeed true. So if I know this, okay, if I give given the next question is how to find it, and the last question how to find all of them. Now, the only question we can already answer is how to find all of them. Okay, namely, if the function this small f of x is defined on an open interval, and I have an antiderivative, then I know that all other antiderivatives are related to the antiderivative I have already found just by a constant. Okay, so we have proved this already. So let f be an antiderivative of f on an open interval let's say AB, then all antiderivatives are given by f of x plus c, where c is a constant. Okay, so even this result is not completely trivial. Okay, as we know, you need just to remind you, we use the mean value theorem in order to prove this result here. Okay, but this tells you that if you have already if you have already found one antiderivative, okay, then you can find all of them. It doesn't tell you how to find this one, and even what is a more serious problem is, okay, it doesn't help you in order to identify which functions small f indeed do have antiderivatives. Okay, so but this reduces the task. So for us now to guessing. So for instance, if you choose x squared, okay, it's easy to guess the antiderivative, of course. So f of x is equal to. So this is the antiderivative, and from this result you know that all antiderivatives are given by f of x plus c. Okay. So actually, because we have already learned for quite a lot of elementary functions how to compute a derivative, now just by looking, so if we look, for instance, at the table which tells us for every function the derivative, by looking at the table in the other way around, okay, we get now this results for antiderivatives. Okay, so you can, for instance, we also get general results. For instance, if you know the antiderivative of f of x, if you know that the antiderivative of f of x is equal to large capital F of x, okay, then you can also find the antiderivative of this function, namely c times f of x is the antiderivative. Okay, so this essentially is one of the rules for differentiation. Okay, read in the other direction. Now you find a table in our textbook. I just want to mention some of them. For instance, 1 over x. What is the antiderivative? What is the antiderivative? Should be easy, right? So what is the antiderivative? The logarithm of x on which interval? This is the question you have to ask for antiderivatives, because of course ln of x is true, but just for positive x. So you can also say this is an antiderivative, okay? But here actually the domain which I look at is different. So here I look at all numbers not equal to 0. Okay. Now it's for this function it's not if the domain of this function if the domain of this function is this domain here. Okay, so the question is, what are all antiderivatives? Now you see that okay, all those functions are antiderivatives. Okay, but are those all antiderivatives? Actually, this is pretty easy. So if you want to find antiderivatives, because you know that if x is larger than 0, so all numbers larger than 0 is the open interval, then all antiderivatives for x is larger than 0 are ln x plus a constant, and if x is smaller than 0, then ln minus x, okay, but plus another constant. Okay, so actually those are all antiderivatives. Okay, because I look at the domain, I look at the domain as minus infinity to 0 and 0 to infinity, and I use the theorem which I just showed you for this and for this part. Then I get that those must be all antiderivatives of this function ln of 1 over x for this domain here. So actually, if you are interested in finding all antiderivatives of a function, okay, it's also important that someone tells you what is the domain. Okay, because if you just look at this function 1 over x, for instance, if your domain is, for instance, this interval here, 0, 1, then all antiderivatives are ln x plus a constant. Okay, so it depends what is the domain of this function. Okay, so if I ask you what is the antiderivative of 1 over x, actually your answer should be a question: what is your domain? Okay, so you see that, but actually, by reversing the process of differentiation, we easily get antiderivatives. Now, for instance, if you look at this function here, okay, so it's easy to guess here antiderivative. So most of you are certainly able to guess that the antiderivative is e to the x square half. Okay. Now, okay, how about this one? So let's say x is any real number. Okay, so here maybe it's a little bit more complicated, more challenging to guess the antiderivative. Okay, but you should be aware maybe that there doesn't even exist the antiderivative. Okay, it's another possibility. As I said already, okay, we will prove later on that for all continuous functions in fact do have an antiderivative. So this then means that this function, because this function is continuous, okay, does have an antiderivative. For instance, also this function here, because it's continuous, okay, has an antiderivative. Okay, but here this is even more complicated for this one to find it. Now, something what we indeed can do is, if we have, for instance, for this function, okay, so maybe some of you can guess what the antiderivative is, but if we do not know, if we do not find an expression for the antiderivative, what we can do is we can try to find it by plotting the graph. This is something we can always do. So if you look at this here, okay, so this function here, if you plot it, okay, so we have here 1. Okay, now finding an antiderivative, because we know that it's not necessary that there is only one. Okay, there are certainly many. Okay, because we know that all antiderivatives, once we have one, okay, are given from the one we have already found plus a constant. Okay, so actually we can shift them and still have antiderivatives. So if we want to find the antiderivative, we have maybe to say we have to give one condition. Okay, so for instance, let's say we are interested in the antiderivative, which at 0 is equal to 0. And now from the graph, this of course is indeed possible. So we know that we have that the original function. So this is our f of x, and we want to find the antiderivative. Now we know the antiderivative starts at 0. Okay, and this here tells us. Okay, so for x is equal to 0, what we have 1 here. So the value tells us, okay, how we have to proceed from this point here. Okay, so at 0 we see the value here is 1. So what we have to do is we have to essentially walk in the direction 45 degrees. Okay, and as we keep on walking, because this always tells us how to go on. Okay, as we keep on walking, okay, because this here is the slope at the tangent at the point where we are at the moment is getting smaller and smaller. But since this is always larger than 0, this function must be increasing. So we kind of guess, okay, so it could look something like this here, and also something like this here in the other direction. Okay, so this would be one possibility. You do not find the antiderivative still to figure out the antiderivative by plotting a graph. Okay. Something which is related to what I said, which is essentially the same, but which is quite often used, is the so-called direction field. So as you have seen here, okay, so actually the function f of x gives us for every point, so for instance for this point, the direction in which we have to walk. Okay, so for if we do not have this initial condition, then on this line the direction is always 45 degrees. Okay, so what we do is we plot here just the direction. Okay, and then we proceed like this. So we choose another line. For instance, 1 here. Okay, so we choose this line here. So for 1, you see the direction 1/2. Okay, so you have something like, it's getting a little bit, so it's not so steep as this one. And then it's getting even, as x is getting larger and larger, the slope here is tending to 0. Okay, so you have something like, maybe here you have something like this here. I don't know. It's still positive, of course. I'm not very good in drawing something like this. And in the other direction, you have the same. Okay, so for instance, at -1, you have the same here because it's symmetric. Then it's getting even. Okay, and if you now want to find, if you have an initial condition, okay, so this, for instance, this initial condition here means you start here. Now you can find your way through the direction field, okay, by just walking into the direction which the direction field gives you at the point. Okay, so it's roughly like, okay, and we should get the same graph. Okay, now this so-called direction field is something which Maple can plot. So you can give a function, you can give Maple a function and tell Maple plot the direction field. Then you get the direction field, and then you can find graphically, okay, the antiderivative. Now, as I have said, for this function here, okay, maybe if you spend some time thinking, okay, you will discover, okay, the antiderivative is 2 times the square root of absolute value of x minus ln 1 plus square root of absolute value of x. Okay, so we will later on learn techniques, okay, how to find this, but for now, if you take the derivative, okay, we'll easily see, okay, this is indeed the derivative of this function here. Okay, and so for here, it's not really necessary to do it graphically, but more easy. Now for this function, it's much more challenging, okay, because nobody ever, there is an antiderivative, but it's not possible to write it down in the functions we know. Okay, so here is much more complicated. So here you actually have to stick to some software in order to find antiderivatives. Okay, so the important thing about this section on antiderivatives is, okay, that for some function it's complicated to figure out the antiderivative, but we still can do it graphically. Okay, we can always find the antiderivative, and this is the first important thing. The second important thing is if you are able to find by guessing an antiderivative of a given function. Okay, we know that if the given function the domain on which you consider the given function is an interval, an open interval, then all antiderivatives are given by the one which you found plus a constant. Okay, but there are still 2 questions left. Namely, the first question is, okay, for which function? Okay, is there some criteria, some easy criteria to figure out for which function do I have an antiderivative? Okay, because if a function does not have an antiderivative, I do not have to search for it. Okay, it's the first thing. And the second thing is, okay, if I know that that for certain classes of functions satisfying certain properties, there are antiderivatives, how to find them? This is the second question. Okay, and those 2 questions we will solve in the next section, in the next chapter, chapter 5. I should say we will solve them. We will give an easy solution of them. But those 2 questions are more or less completely solved. But you will maybe learn more general results in more advanced classes of mathematics. Maybe some of you might wonder, why do I call them antiderivatives? Because in high school we just use the integral sign. anyway, if you know it, okay, in high school, maybe some of you have learned, okay, the integral is also more or less the antiderivative, okay. The reason why I make a difference here between those two, okay, will become apparent later. And it's something which is important for the sequel. So you should, as for now, you should forget what you have learned in high school about integration. Okay, so, but let's do an example which maybe demonstrates the use of antiderivatives. You can find this example in your textbook. Okay, so a ball is thrown upward with a speed of 48 meters per second from the edge of a cliff (430 meters above the ground. Okay, so essentially I use the same example as you see in our textbook. I just changed the units because our textbook, this is an American textbook, so there are feet per second. I'm not so used to this kind of stuff, so I'm using meter instead of it. But actually, this 48 meter per second would be, this velocity is very large. Okay, so maybe it's not possible by hand throwing it that fast. Actually, this is just physics. So in physics, you have learned that actually this information is enough in order to describe the position of the ball after time t, because from physics you know that actually the only thing you know here is the acceleration, because the ball is subject to the gravitational force, and you know that once you throw it up, okay, there is a force acting on the ball which will put it down, the gravitational force. And you know that the gravitational force will cause a velocity of minus 9.8 meters per second square. But we do not need the units here. So this is essentially what you know, okay? And now, since you so this means, because we want to, for instance, know the position function, okay? So this is everything we need, okay? Because we know that the acceleration is the derivative of the velocity. So we have to find its antiderivative, then we have the velocity, and then we have to find the antiderivative of the velocity, and we have the position function. Okay, and here what we have here are the initial conditions. So from this here, so this depends actually on the time. Now we know that, okay, so the velocity function is the antiderivative, which is easy to guess, plus a constant, okay, and we have that at time 0, okay, this is the initial velocity, so this will determine the constants. So we see that v of t must be equal to minus 9.8 t plus 48. Okay, and if we want to have the position function, we have to find the antiderivative of this function here, which is minus 4.9 t squared plus 48t plus another constant. And this constant is determined by the initial position. So you get that s of t is equal to minus 4.9 t squared plus 48t plus 432. Okay, now you can discuss all kinds of questions like, okay, at which time t does the ball reaches the highest position? What is the highest position? When does it hit the ground? And so on. Okay, so essentially, this is physics here. Okay, this was observed by Newton, that the only force which is important is the gravitational force, and the rest is calculus, finding antiderivatives in order to describe the position function of such a ball. Okay, so this just should show you, okay, that that the notation of antiderivatives is something which naturally occurs in application and which is important. Okay, so any questions to this? Now, the next thing is we will go on to chapter 5 and to introduce integration. I'm aware that you, in other classes, you already needed quite a lot of tools from the theory of integration. So, but in chapter 5, what is essential for us is to give precise definitions. This is something which you might not have seen before. Actually, the way our textbook is organized is a little bit strange because in order to define the integral, what we need is actually sequences and limits of sequences. So I just say maybe a few words about this before I go into the details of section 5.1. You will find this much later. Okay, this is in chapter 11, but actually is needed for chapter 5. So this is a little bit strange in the textbook. But there is no big difference to limits. So you have learned in high school what a sequence is. For instance, a very easy example is like this. It's an easy example for a sequence. Actually, a sequence is just a function, but the domain is now restricted to the natural numbers. This is a little bit similar to the functions we have considered so far. In particular, if you plot this sequence, you will observe that okay, so you plot it as a function. Okay, so you consider it as a function with domain being natural numbers. So you have here 1, 2, 3, 4, and here is 1. Now, if you plot the sequence, you will observe that at 1, okay, you have 1/2, and then it's getting larger and larger. Okay, but always remains under this line here. Okay, and essentially what you will observe is that as n is getting larger and larger, this sequence here seems to tend to 1. Okay, so you have here something similar to the limit. Okay, now since this is similar to the limit, okay, we have to give a precise definition. Our precise definition is the epsilon delta definition. Okay, so we define for a sequence. Now this is completely similar to functions. Okay, so we say that the limit of f of n as n tends to infinity is equal to some L. Okay, so what does this mean? So just the same as you see here. Okay, so what does it mean? It means that for all epsilon larger than 0, okay, there must exist n which might depend on epsilon, okay, such that the difference between an and L will be smaller or equal than epsilon whenever n is just larger than n. Okay, so this is similar as the definition of the limit of f of x as x tends to infinity. It's just the same definition. Now, you also know from high school that if such a limit exists, we will say that the sequence is convergent, and if the limit does not exist, the sequence is called divergent. Okay, and for divergent, so if limit an exists, then an is called convergent. Otherwise, an is called divergent. Now, for divergence sequences, okay, we have a special definition as we had for in case of functions where the limit does not exist, namely the special situation where where an is getting larger and larger. Okay, so the limit of if an is getting larger and larger as n is getting larger and larger, then we will say that the limit of an as n tends to infinity is equal to infinity. Okay, so it's divergent. A divergent sequence. The limit does not exist, but it does not exist in a very special sense. Okay, it's just the same as for functions. And you can give a similar definition, epsilon delta definition for limit n tends to infinity is equal to infinity. So similar to functions, we define limit n tends to infinity of a of n is equal to infinity. Okay, now as for functions, as for the limit of functions, the first question we discussed was, okay, how to find now for a given function, how to find the limit. Now the strategy we used for functions was, first we figured out for some simple functions how to find the limit, or we found some simple limits, and then we found some rules how to build from simple limits to get more complicated functions. Of course, we do the same here. Now, as you see already from the definition here, there is a close connection to functions. Indeed, a very important but almost trivial result is the following one. If you have a function f of x, okay, so if you have the following, if the limit of f of x as x tends to infinity, okay, is equal to some L, and you define an to be equal to f of n, okay, then of course the limit of an as n tends to infinity is also L. Okay, where here you use the definition we have seen in chapter 2, and for the conclusion you use this definition here. Okay, so then the limit of a of n as n tends to infinity is also L. The inverse is not true of this result. Okay, it's not necessary that if you have a sequence, you know that the limit is equal to L, and you can find the function such that f of n is equal to a of n, that this limit must exist is not necessarily true. You can think about it. It's easy to find the counterexample. So the inverse here is not necessarily true. Okay, but this is already helpful because this already gives us limits of simple sequences just by using this principle here. Okay, so now, for instance, the limit of 1 over n to the r as n tends to infinity, we do not have to use the epsilon delta definition to prove that this is equal to 0 for all r is larger than 0. We just have to use this. We can just use this result here. We observe that if we have a function f of x, if we choose f of x to be 1 over x to the r, since we know that this limit is equal to 0, this limit will be equal to 0 as well. Okay, so you see, this here is trivial, almost trivial. Okay, you can prove it easily from the epsilon delta definition, but it gives us already limits of many, many functions. Okay, the first thing. The second thing is to observe that, okay, because the definition is so similar, okay, it's no surprise that all the limit laws still hold for limits of sequences. Okay, so all limit laws hold for limits of sequences as well. Okay, so for instance, you have the squeezing theorem. You have that if an is larger or equal than bn, the limit of an exists, the limit of bn exists, then the limit of an must be larger or equal than the limit of bn, and so on. Okay. So and the proof of all those results just the same as for limits of functions. Okay, because the definition is similar. So you can just rewrite the proof. Okay. Now, just because I quite oftenly see that, okay, so if you For instance, if you have this here, okay, and you have to find the limit, so what is the limit here? Okay, now everyone will say I use the L'Hopital, okay, but it's not possible here because it's not a function, okay. We haven't defined derivatives for sequences, okay, so it's not possible here to use the L'Hopital, but of course it's the idea is correct because you can use this result here, okay. So you just observe that, okay, you first look at the limit x tends to infinity of sine of 1 over x over 1 over x. If this limit exists, it must be equal to this one, okay, and here you can use, so this is the limit x tends to 0 of actually, okay, 0 from the right, sine of x over x, and this limit is equal to 1, for instance, by the L'Hopital, or we have also found another proof for it. So now you can use this theorem and conclude this limit is also 1. Okay? So actually, for something like this, you can think about, you can use the L'Hopital, okay? It's not completely precise. Actually, what you are going to use is such a result here. Okay? So in this sense, the rules of the L'Hopital can also be applied for limits of series. Okay? Whenever you are able to find such a function. Okay, so any questions to this? So essentially for sequences, because in some sense, sequences are just functions, okay? Sequences are functions where the domain are the natural numbers, okay? So, but in chapter 2, we have looked at functions where the domain are real numbers, okay? So the limit here is a little bit different, okay? But from the definition, you see already that they are very similar. This is clear because a sequence is nothing else but a function, okay? And from this result here, okay, it's easy to you do not have to prove this by going into the epsilon delta definition because we have proved it already for the function 1 over x to the r. So this result will help you to figure out limits of lots of the elementary functions. Then you observe that all the limit laws hold, and then you can do the same building process as we have already done in chapter 4 in chapter 2 in order to compute more and more complicated limits. Okay, so this is what we will need in the sequel. So any questions to this? I don't know why the author has organized the material in this way because it's not very the organization is not very good because in chapter 5 we will see in a minute. We will already need the series of sequences, which is from chapter 11, I think. I'm going to look at areas and distances. Okay. Now, what we are going to discuss in the sequel is we are interested in order to solve the area problem. The area problem is a problem which emerged in the 18th century, so a quite old problem. So we have a given function f of x where x is, let's say, on some interval a, b. And the question actually is very easy. We also assume that the function is larger or equal than 0. So, okay, so let's say this is our function. Okay, so you have already discussed this in high school. The question which we want to solve is, okay, so how to find the area below the function and above the x-axis. Now, this question looks pretty innocent, but maybe it's good at this point to stress that maybe in high school it was introduced like this. Okay, so we have a function which is larger or equal than 0, and we want to find the area. Okay. Now, actually, because in high school maybe it was not discussed that this question like this doesn't make any sense. Okay, because we cannot find something which we haven't defined. Okay. So actually, the first question we would have to ask is, okay, how to define the area? Now, this is not an easy problem, and there is we will solve this for some special cases, but maybe later on, maybe once you you get into graduate school, you will discuss this problem much more in a much more theoretical sense. So there is a theory in mathematics called measure theory which just discusses this problem. Okay, how to define area of some given sets. Now it's not a very easy question. Okay, so actually what we want to do is, it's not that we want to find the area. This is maybe what you have done in high school, okay, but the teacher never told you that first you have to define it. Okay, what we want to do is we want to define the area. It's pretty different. Okay, so our main question is, okay, how to define this area. Now, in high school, you have already learned, if you have some simple objects, okay, so for instance, you have this object, okay, a rectangle. Now, the area of this rectangle, maybe in high school, your teacher tells you that the area of this rectangle is A times B. Actually, this is the definition. We define the area to be A times B. It's not that this is the area. This is the definition of the area. It's pretty different. Now, if you have, for instance, the next case normally is, okay, if you have a triangle, then you can define the area. Also, this is a definition. So you define the area as C times H half, the definition of the area. Okay. Now, normally in high school, you discuss many problems where you have some more complicated objects. Something like this here, and you have to find the area. And what you do in high school, normally you divide it into rectangles, and you compute then the area by computing the by using this definition and computing the sum of the area of the rectangles. So I shouldn't do this. Sorry. So if this area is A1, this area is A2, this area is A3, this area is A4, then the area of the whole thing is A1 plus A2 plus A3 plus A4. Actually, also a definition. Okay, we define the area of something like this here as the sum of the areas of simple objects we have already defined. Okay, and now in general, okay, if we want to define this, it should become already clear how to do this from this easy situation. This is something which the Greeks already tried to do. Namely, the next more complicated object is a circle. Okay, so how to define the area of a circle, or normally what the Greeks discuss is how to compute it. Okay, now but this is the same as defining it. You inscribe triangles. Okay, as many as possible. You compute the area of the inscribed triangles, okay, and make the subdivision finer and finer, okay. So in the limit, this is something which the Greeks have not considered the limit. That's why they couldn't find the area of the precise area of the circle, okay. So what you need here is the limit notation, okay, naturally. So, the same approach we use here, okay. So actually, since for this simple object, we know how to compute the area. So what we are going to do is we inscribe such objects inside this, what we see here. We compute, instead of this area here, we compute the sum of the area of the inscribed rectangles. Okay, and then we make the subdivision. We inscribe more and more rectangles. And in the limit, okay, we will get the area, or differently, we will define the area by the limit. Okay, so this is essentially what we want to do.